Siz.
Yok, ben burada kısık kapatmıştım. Değerli katılımcılar, hepinize günaydın. Çalıştayımızın ikinci gününe hoş geldiniz. Bugünkü konumuz deprem yalıtım sistemlerinin ve titreşim sistemlerinin endüstri tesislerinde ve güçlendirme uygulamalarında kullanılmasıyla ilgili olacak. Programımızda son dakika değişikliği oldu. Saat 10'da uzak bağlantıyla Yoshio Matsubara bir sunum yapacaktı bize. Fakat bazı aksaklıklar nedeniyle kendisi katılım sağlayamayacak. Onun yerine saat 10.30'da şu anda Doktor Fatih Sütçü'nün sunumuyla başlayacağız. Fatih Hocam, sizi rica ediyorum buraya. Kulaklıkları ayarlayalım.
İngilizce yapacağım. İngilizce yapacağım.
Öyle mi?
Yani,
tamam.
Yok bence.
Yine de kulaklıkların sonraki sunumlarda ihtiyaç olacak.
Tabii ki. Biraz şöyle yapacağız. Japon.
Hocam ihtiyacınız olursa.
Tercümanda sorun olabilir.
İhtiyacınız olursa.
Tamam hocam, sağ olun. Evet. Herkese günaydın. Japon misafirlerimizin kulaklıkları gelene kadar bir dakika bekleyelim. Ben sunumu I will make this presentation in English, but for the next presentations they will bring you the headsets. Evet, herkese günaydın. Good morning, everyone. Ohayou gozaimasu. Today, I will talk about the recent developments in external structural seismic retrofitting methods. First of all, I would like to thank the organizers for this event, and I also would like to present my gratitude to our Japanese guests and all of you guests here joined today. And because this workshop is about the recent developments in Japan and Turkey, although there are several seismic retrofitting methods, I will basically talk about the seismic retrofitting methods that we are working in Istanbul Technical University in collaboration with Japanese universities or companies or technology developers together. And so in this first slide, I would like to talk about the Vitruvian Triad. The first time I heard about this is from Professor Wada several years ago. And this is a Roman architect who lived before Christ, like 2 centuries before Christ. And he said that a building should be strong, functional, and beautiful. And yeah, we all agree with this. Although he was the architect of the emperor, so he didn't have much concerns about the cost of the building. And also, they were not concerned about the environmental impact or energy efficiency or the sustainability of the building. So maybe a new rule can be added in our recent world that a building should be sustainable, which translates as it should be economic, cost efficient, energy efficient, and environmentally friendly. While this is true for new buildings, so how about the existing buildings? So maybe innovative retrofit method that improves these qualities should be required, because generally when we retrofit a building, we interfere with the building too much. And although the building becomes stronger, it is not necessarily economic or it is not necessarily energy efficient when we use conventional retrofitting methods. So which type of buildings should retrofit? So in our studies, we generally concentrate on governmental buildings, like schools, hospitals, or other type of governmental buildings, because these buildings are more important than other buildings. I don't mean that residential buildings are not important, but what I mean is during a disaster, a school contains lots of students. They're important for us. And after a disaster, a school building can be used as a shelter. So that's why these buildings are kind of more important than, let's say, not important, but these buildings have priority to be retrofitted. Let's start with an example. This is a very typical school building in Turkey. And there are thousands of similar buildings built with similar plans in many parts of Turkey. So what I mean by external retrofitting is this. Say, this is the model of the building. First, this is one of the options. First, we install steel members along with the columns, the existing columns of the building from outside, and then the beams are introduced. These are steel beams also attached to the existing beams of the building, also from the outside of the building. And then these are, in this example, this is a buckling restraint brace, a special type of brace which can dissipate seismic energy during an earthquake motion. This can be applied in several configurations depending on the demand, the seismic demand of the building. It can be a full retrofit, or it can be applied on half of the spaces, or it can be applied partially to the building depending on the demand. Other types of dampers are also available in the world. This is a toggle type of damper which amplifies the displacement of the building and it translates it in a larger displacement in the damper. So the external retrofitting improves seismic performance, and it makes minimum interruption to the occupants or the business or whatever is going on in the building. If it's a school building, it can work as a school. If it's a hospital, it can work as a hospital. There is a slight noise problem, but with new tools, we can reduce the noise during the application. And this can be a good opportunity for us to improve the thermal performance and the visual of the building, because we have already installed a new facade to the building. Actually, this is a kind of a new opportunity. Now we have new construction outside of the building. We can add new facade on this building to improve visual and thermal performance of the building. This is one example that we have already completed in Istanbul Technical University. This study was completed in collaboration with Tokyo Institute of Technology, with Takeuchi Lab and Nippon Steel as the manufacturer of the BRBs. This frame is the same frame in the same scale, almost same scale with the school building that I have just shown you, using same materials, same aspect ratio, and BRBs are installed in this frame, and seismic motion is simulated by using this experimental setup. We built these frames in Turkey by using Turkish technology, just as it was built in Turkey, and all of the BRBs and steel members are imported from Japan for this project. And first we did the RC frame only test, and then we added the steel members and did test again, and then BRBs are added. And another application is, you see this frame is concentric within the building frame, within the building plane, and we can also use an external type, which is this. In this one, you can see that the frame is added from the outside of the existing frame. And these are the performances. I will not go deep into this, but you see in the RC frame, the stiffness is quite low, and after the steel members are added, the stiffness gets higher and it shows some energy dissipation. Later, when the BRBs are introduced, the seismic energy is dissipated by the BRBs. And when the BRBs are introduced externally, the performance is much or less the same. This is one example about the equivalent damping. Before the retrofit, in the reinforced concrete frame, the equivalent damping is approximately 5-6%, around 5-6%. And after the BRBs are introduced, approximately 15% damping is added, which is quite valuable during the design of this building and retrofit studies. I will show a small video during the BRB tests. I will move forward. Yes, here during the loading, you can see that the BRB is, there is a steel core inside the tube and it stretches along with the loading protocol. Here we have reached almost 1% cycles. Here you can see the stretch. And all of the energy is dissipated by the BRB core, the steel core. And you can also see that the cracks are distributed along the reinforced concrete members. Yeah. Here is an application in Japan. This is Tokyo Institute of Technology, the Midorigaoka 1 building. I have worked in this building for almost 2 years. This building is built around 60s. The concrete quality is questionable. The structural system is fairly good, but it needed retrofit. So the proposed method is to add BRB members outside the building and also some louvers outside the building, which will improve the performance, the thermal performance, and also the visuals of the building. These are some application photos, and this is the final condition of the building. Now this building is safer, stronger, but I believe it also looks more beautiful, which is also proven by a design award that is given to this building. And 2 professors are shared this award in Japan. I use these images by the permission of Professor Takeuchi. By using the louvers, okay, this is not seismic, but this is an opportunity to improve the thermal performance of the building by using the louvers. In the summertime, the louvers cut the direct sun radiation, but in the winter, it lets more sun radiation inside the building, which increases the thermal performance of the building. This kind of analysis are also done in Turkey. Please remember that this kind of analysis is made by architects in Turkey. In Japan, this is made by structural engineers. That's it. That's a slight difference. And computational fluid dynamics analysis is made to see the effects of the added facade to the building. So when you have the louvers inside of the building, in front of the building, you will have a thermal buffer in between the building and the out environment. So what we do here is, say the building has 1 lifetime, and instead of demolishing and building again, we retrofit the building and we give another lifetime chance to the building. This can be considered as recycling. We recycle the building. We use the building again by retrofitting the building. And also, when a new facade is added, the building is visually upgraded and the daylight effectiveness is improved, etc. But meanwhile, we should be aware of the fact that this application should be done carefully, where the dampers should be accessible and it should be easy to clean the building. And the seismic resistance of the facade is also important. I mean, the building is okay, but the facade should also be seismic resistant. And in case you need to change the dampers or say replace the dampers after a big seismic event, it should be easy to disassemble this facade and then install new dampers. So this is kind of a concept study. We recycle the building, we upgrade the building. This can be called as an upcycling concept. There are many facade proposals. Here I will show you one of them. Say the building is externally retrofit by a kind of damper. It can be BRBs, it can be oil dampers, or any kind of dampers. And then a new and simple modular system is introduced from outside the building, and the new facade is introduced. These are all modular members. They can be removable easily in order to access the dampers easily. Another alternative is to add a kind of mesh outside the building. This can be used for green screens, like a plant type of facade. it should also be easy to remove this kind of grids or mesh type of facades. Okay, this was our first project. And in our second project recently, as Istanbul Technical University, we are working with Mayda Corporation and the Turkish Ministry of Environment and Urbanization for another external retrofit project. This is called Master Frame Retrofit. This is simply adding new reinforced concrete frame outside the building. And this one is an example from Hokkaido University. This is the before picture, and this is the after picture. You can easily see a new facade is, a new frame is introduced from outside of the building. Please keep in mind that all of the facade applications are also available when you use this kind of technology. You can introduce a new facade in front of this frame, or you can even introduce dampers inside this frame. So this is just an interface, actually. But even itself, it is improving the stiffness of the building and also ductility of the building. So this system is widely used in Japan for retrofitting buildings externally. So what we do is to install the new frame, which is just a conventional reinforced concrete frame, cast inside frame. We install the frame by using special disc anchors developed in Japan. Recently in Istanbul Technical University laboratories, we are doing the shear and pull-out tests of this special type of anchors. Because of the disc head of the anchor, the shear capacity is quite larger compared to the conventional anchors. And that's why the number of the anchors used will be much lower. And it means the application time is shorter, it will be economical, and the noise will be quite lower. And these are the tests. I will just shortly show you some tests. And here in this setup, we are using this setup for doing the pure shear tests on the disc anchors. And after the shear capacity is confirmed, we do a pull-out test to see the pull-out capacity, the residual pull-out capacity of these disc anchors. Because after a seismic event, when the disc anchors are subjected to lots of shear force, and after the seismic event is finished, we don't want the frame to disintegrate from the building and fall down. So even after shear capacity is reached, we want to show that these anchors still have residual pull-out capacity. And we have already shown with some tests that these anchors has lots of residual pull-out capacity. So they are quite reliable anchors. These are some photos from the test that we have already completed. I also would like to mention that these tests are conducted on several types of concrete grades. In this first test, we used an 8 megapascal concrete block, which is quite low. And it is already shown that these disc anchors shows quite good performance on even low strength concrete. In the coming tests, we will use higher grades of concrete like C12 or C16, which is widely seen in the building stock in the Turkish school buildings or other governmental type of buildings. By the way, I would like to mention that even though we are concentrating on school buildings or hospital buildings, it is also possible to use this kind of external retrofit technology for residential buildings or any type of buildings. It is the only point is that these buildings should be regular in plan. As long as it's regular in plan, it is easy to attach a single monotonic frame from outside and improve the seismic performance of the building. And we are also doing some analysis, nonlinear performance analysis on the building models by using this external master frame retrofit technology. We have already completed most of our study, and hopefully next week we will visit Japan and meet with JICA, because the sponsor or the supporter of this project is JICA. We will talk about the findings of our research project for the last 1 year. And finally, this is another one. It looks similar, but it is different. This is also an external frame retrofit technology. Here you can see that there are small dots here, points here. This is a precast. It is not very clear here, but you can see that these are assembled precast columns and beam members. And We are also conducting some research on this external retrofit technology. This is a patented technology by Japanese Kurosawa Construction. PC means precast post-tensioned concrete. And this frame is, first of all, it's precast, prefabricated, and brought to site and attached with each other and also with the building by using post-tensioned bars. It is similar to the previous technology, but there are some differences performance-wise and cost-wise. So, but the important point here is that we see that in Japan, many external retrofit technologies are developed, and we need such technologies to retrofit some school buildings while there's education inside. Because in Istanbul, maybe it's possible to evacuate a building and move students to another school for 1 year or 2 years, and then you can retrofit the building or rebuild the building. But in many cities or towns in Turkey, it is not possible to remove all the students and stop the education for several months while you are doing the retrofit works. So in that kind of buildings, we need this kind of technologies without interruption to the occupants. And yeah, this is a very simple figure about the post-tensioning technology. All the members are disassembled and brought together, attached by post-tensioning bars, and the retrofit studies are complete. Okay, thank you for your attendance. Thank you for listening to me.
Teşekkür ediyoruz Fatih Hocam'a. Bir sonraki sunumu yapmak üzere Sayın Koji Nishimoto'yu sahneye davet ediyorum. HDMI or VGA?
HDMI.
HDMI? Sorry, VGA you have?
Yeah.
Okay. Do you need sound?
No.
No, okay. That's mine.
Sorry.
I can give you if you want.
No.
Do you need it? You don't need it?
Wait a moment, please. Sorry.